Hey everybody, today I'm going to be talking about classifying employment status from data obtained by the Human Resources Office. The Human Resources Office is a vital asset in almost all businesses and companies, and they oversee hiring, administration, and training of new personnel. In addition to these responsibilities, HR representatives also oversee employee compensation, administering benefits, performance appraisal and management, employee and labor relations, as well as compliance and discipline management. This project will utilize various HR-related features to train an algorithm to predict whether an employee will be terminated based on information collected by human resources representatives during the hiring process and throughout the employment of the employee. The data comes from a source on Kaggle.com. Two professors, Dr. Carla Patalano and Dr. Rich Huebner at the New England College of Business, set out to find a data set using human resources information in order to aid their students. They found that most of the time, HR data lags in real-time information and is often not updated frequently or accurately. To give their students a meaningful data set, the pair decided to create an HR data set revolving around a fictitious company called Dental Magic. They included pertinent features that their students could then visualize, primarily using Tableau. The dataset itself can be broken into two major categories. The first is personal information, which contains name, age, date of birth, sex, marital status, citizenship, race and ethnicity, and the state and zip code in which the employee lives. The second category is more focused around employment-related data such as employee number, date of hire, date of termination, employment status, department, position, pay rate, supervising manager, employee source, and performance score. This is plenty of information to be able to create a machine learning model, and the feature that I'm going to be trying to classify is the employment status of each employee. The biggest potential challenge for this project is that my data set is very small. It only has 301 entries. And the second issue is that of the 21 columns that are given, only 4 of them are numeric variables. That means the rest of them are object variables or strings, and it will require a lot of preparation in order to analyze this data set. And I'm going to be preparing the data set by using the get dummies and one-hot encoding of the categorical features. So an overview of my plan is to talk about the data exploration and the manipulation of the data, the feature engineering and extraction that I performed and able to gain more valuable features, the 4 models or algorithms that I decided to use: decision trees, random forest, logistic regression, and the k-nearest neighbors, and then I will evaluate them and conclude at the end. So the first data exploration that I did is checked for missing values in the data set. As you can see, the date of termination column has a substantial amount of missing entries. And this makes sense because we're looking at an employment data set. Obviously, not all of the employees have been previously terminated. And so, many of them probably still work at the company. In order to deal with these missing values, I just dropped the date of termination column, because if I'm trying to predict the employment status, I don't really want to know the date of termination or if they've been terminated at all. So I dropped that entirely. And then for some reason, the entire bottom row of the data set is full of empty values. So I just dropped the last row as well, just to easily take care of that problem. Another way that I prepared the data set was that I dropped unnecessary, valueless, and redundant columns. For example, I dropped the date of birth column because I also had the age column, so that was kind of like a redundant feature that I didn't necessarily need. And I also dropped the employee number, the date of termination, the state and zip code, the employee name, and the reason for termination because they don't really add any value to. I also transformed the yes and no, male and female, and employed and terminated column entries into binary responses where male equals 1 and female is 0, yes is 1 and no is 0, and terminated is 1 and active is 0. After the simpler binary responses were transformed, then I had to look at the date of hire column. In the date of hire column, as it is, doesn't really give much meaning to how long the employee has been there. So I turned that into a date time object, and I'm going to talk more about the date of hire in the next slide. And then for the remaining categorical features, I applied one-hot encoding to the marital status, citizenship status, race, department, position, manager name, and employee source. Applying this method has some pros and cons, one positive being that the machine learning algorithm can now include this categorical data because it is numeric in nature now. But the con is that the data frame went from 21 columns to 70 columns. This giant increase in the size of the data set would add to the computational complexity of the algorithm if it was not such a small data set that I'm using. So for the date of hire column, I wanted to change it to days of service because I feel like that's a much more like tangible number to get a feel of how long an employee has been at the company. And so this was done by converting the date of hire column to a date time object and then creating the new days of service column as a time delta object using a more current date minus the date time object, the date of hire in that column. And so then the days of service is a time delta object, and then I just converted that time delta object back into an integer value. This data set is unbalanced as it's given. About 2/3 of the employees listed in this are still active, and only about 1/3 of them have a terminated status. And in order to combat this, I created masks where the employment status equals 1 or 0, and then assigned these variables to, or assigned them to variables called the majority and minority, depending on which one it was. And then I resampled the minority variable, which was the employee status equals terminated variable, in order to balance the number of observations in each class. And I did that with replacement. And then once these two variables had even numbers of observations, I then concatenated them back together to create the final process data frame that is ready for analysis. The data set will then be split into the features, which is all of the variables except for employment status, and then the target will be, of course, the employment status, and these are split as X and Y respectively. And then I'm going to perform a train test split to create the training set and testing set for each algorithm. The decision tree classifier uses either classification or regression techniques in the form of a tree structure. It breaks down the data set into smaller branches based on particular criteria about the data set. As the tree grows, the model is developed and eventually returns a trained model with nodes and leaves. My initial baseline decision tree classifier without any tuned hyperparameters yielded a 77% accuracy score on the testing set. This is a decent accuracy score, but the tuning of the hyperparameters for the algorithm would likely yield a slightly higher score. The hyperparameters that yielded the best results were setting the random state in order to get replicable results, as well as setting the max features to log 2. This means that the maximum number of features the tree will consider are the log base 2 of the total number of features in the data frame. This hyperparameterization yielded an accuracy score of 83%, so that's a pretty significant increase. And as we all know, the accuracy score is not the only way to validate an algorithm. Viewing the confusion matrix seen here is another meaningful way to determine the goodness of a model. In this image, 46 represents the number of employment status equals active that are correctly classified as active employees. And the 54 represents the number of employee status equals terminated that were correctly classified. The 6 and 14 represent incorrect classifications. The 14 is considered a false positive, which means that an observation that is actually employment status equals active was classified as terminated, whereas the 6 is a false negative, which is actually an employment status equals terminated that was classified as active. Generally, it is better to reduce the number of false negatives as much as possible. After doing the decision tree classifier, the clear next step is to perform a random forest classifier. And this is an ensemble method that creates a multitude of decision trees and creates a forest. This is a good method to use in order to protect the model from overfitting the training data and thus performing poorly on the testing data. The process of having many trees instead of just one helps to eliminate bias and obvious correlations, yielding stronger results than just one decision tree alone. The baseline random forest algorithm for this dataset yielded an accuracy score of 85%, with the number of estimators equaling 100. One way to tune the hyperparameters of the random forest is to create a function that can cycle through the important features and decide which ones to include in the model and which ones to disregard. These important features are calculated by the built-in method feature importances included in the random classifier. The most important features are days of service, age, pay rate, and the manager name. As you can see, about 22 of the important features can be used to preserve the highest accuracy while also eliminating less important features and thus decreasing the computation time. And if it were a larger data set, this would greatly discount the computation time, but since it's so small, it was a matter of microseconds for my analysis. And then using these 22 most important features out of the 69 available features, I was able to bump the accuracy from 85% to 85.8%. So that's a slight increase, which, it's always good to have any kind of increase. And then again, looking at the confusion matrix, the number of true positives and true negatives are high, and the number of false positives is much lower than the number of false negatives is much lower than the number of false positives. I also tried an ADA boost on the random forest model, but even with varying the levels of the learning rate and the number of estimators, the ADA boosting did not yield any higher results for the random forest model for me. The next algorithm that I tried was the logistic regression. And logistic regression also can be used as classification or regression problems, lending it to be a very useful and sort of like baseline algorithm that a lot of people try first. It kind of like allows you to get a feel for the data without doing a very complex algorithm, so that's one of the benefits of it. And the baseline logistic regression for my data set yielded a 77% accuracy score using all of the available features. After tuning the hyperparameters by performing a grid search in order to get the best combination, the accuracy score on the testing set was only 75% with a C equals 15. As indicated in the confusion matrix, it looks good with the true positives and true negatives being high and the false negatives are low. And then from the logistic regression, there are two methods that can be used in addition, called the select k-best features and then recursive feature elimination, to try to downsize the amount of features that we're using while still preserving the accuracy of the model. In conclusion, using a balanced data set helped to reduce the number of false positives and false negatives in each classification. And the random forest model did marginally better than the others at an 85.8% accuracy. And even though computational complexity was not really a factor in my analysis, I did try to use feature elimination and use as little features as possible in order to, adjust for that computational complexity issue maybe in the future. And the days of service, age, pay rate, position, and manager name were significant features throughout the entire analysis. And then the less important features were whether they were Hispanic or Latino, the employee source, performance score, citizenship, marital status, and race. And as far as future work goes, of course, having more data in this data set would be essential to train an even better model. And then I think that as far as like what is given, I believe that a number of children column could be a good feature to include, because I feel like people that have children would be more inclined to work hard and try to maintain their job security. And I feel like that would be a significant feature and an important feature in analysis if we included that. And then for the next one, for my employment status, there were several different options, like terminated for cause, voluntarily terminated, active, a future start, and leave of absence. And so in my analysis, I included terminated for cause and voluntarily terminated into the terminated status as a whole, and then everything else was in active status. And I think that maybe changing the terminated column to only terminated for cause, and then having the other employment status response to be an active status or voluntarily quit. And so I think that may make a difference on the classification, because you can't necessarily predict when an employee is going to quit. And then another cool thing that would be easy to do with this data set is doing a regression problem, possibly predicting the pay rate based on the sex and the longevity of the employee and all the other features that are included. And if you guys have any questions, feel free to contact me on Slack. And I hope you guys are enjoying being home with your pets and families just like I am. Kalua says hello, and I hope you guys have a good day. Thank you for watching.